Hi everyone. This is it. This is the last unit of the course. This is Unit 12. We are going to do a recap of ordinary least squares, but we're going to do it in matrix notation. So I've hinted along the way, sometimes the formulas that we look at get way too messy, and we can't really keep writing them out when you've got multiple regression with more than two variables. So we're going to talk about how to write out the ordinary least squares formulas using matrices. You might be a little unfamiliar with matrices. I'm sure you've seen them, but once you have it in your mind how matrices work, it simplifies everything else. So it's worth the investment to learn how to use matrix algebra to represent econometrics. And if you go on in econometrics, as I hope you will, you'll need matrix notation for everything that follows. So that's what we're going to do today. And then in the second lecture in this unit, I'm going to do a review of all the major topics that we've covered through the semester. So it'll help you get ready for the final exam. So the end is in sight. Grab your pens and let's get going. So let's start our discussion of matrix notation by looking at vectors. All right, so a vector, you can think of it as a point in space. So if we have a graph that has two dimensions, we have the x direction and the y direction, and we have a point in space, point there. How do we describe that point? Well, we need two numbers. So we need the number on the x-axis, so let's say that's 2, and we need a number on the y-axis, so let's say that's 3. And so this point in space is 2 along in the x direction and 3 up in the y direction. So we can write a pair of numbers, and we can think of this also as the end point of an arrow that's pointing to it. So a vector, you can think of it as a few different things now. It's a pair of numbers, it's the point in space that those numbers represent, and it is the arrow that points to that point in space. And at different times we're going to think of the vector as any one of those things, but the important thing is to realize that they're all equivalent. They're all saying the same thing. All right, so let's draw another little graph here. So again, we've got two dimensions, and we'll mark out some numbers along the horizontal axis and some numbers along the vertical axis. 1, 2, 3, 4. 1, 2, 3, 4. And let's draw two vectors. So we'll draw vector A, which is the pair of numbers 1, 4. So that's A. So that will be 1 in the x direction and 4 in the y direction. And we'll draw the arrow that gets us there. And we'll have another vector, and that's the pair of numbers 2, 3. So 1, 2, 1, 2, 3. All right, so you can see in both these examples, my vector is the pair of numbers, it's the point in space on the graph, and it's the arrow that gets us there. Now, why do we have these different representations? Well, because for different applications, you have different types of interpretation. So in physics, for instance, if you have a gravitational field, a field of gravity, it's helpful to have the arrows in mind because they represent the strength of the force in that particular field, or if it's a magnetic field, for instance, around an electrical cable. The arrows give you a picture of the strength of the field at that point. If you are doing an application in geography, though, if it's mapping, then you may be more interested in the points. So you may want to represent a road in a mathematical framework. So then what you want is a series of points, and then you're going to connect them with lines. In our case, we'll typically be using vectors as data, lists of data. So we've already done that. Think back to when you used the price of oranges in one of our earliest examples. So if you have the price of organic oranges, well, what's that? That's a list of data. Okay, and I forget how many, but it might have been 100 observations. Well, that's a vector. That's a vector of data. You wouldn't be able to draw it, though, because it requires a graph with 100 axes. And we can only draw graphs with 3 axes, because more than that, you can't picture it. So if you have the x direction and the y direction and the z direction, then you might have a point in space like that, and you could describe that with 3 numbers. You have a distance along the x direction, distance along the y direction, and a distance up the z direction. But you can't picture 100 dimensions. So that's a vector, and like I say, it's in our applications in econometrics, we don't usually do it graphically or visually because we're thinking of vectors more as lists of numbers. Now, once we have a couple of vectors, so let's write our vectors out like this: 1, 4, and b equals 2 and 3. So we can do some simple operations on them. If I go back here, you'll notice that when we draw these arrows, there's also an angle in between them. The angle, you can think of that as summarizing the way the two line up. So the cosine of that angle, and this is the only trigonometry we're going to do. Okay, don't worry. You got to remember all your high school trigonometry. This is the only appearance of trigonometry here. So the cosine of an angle is kind of a measure of how parallel these two lines are. So it falls in a scale. Cosine falls in between 0 and 1. Okay, so if the two lines are parallel, if the angle between them is 0, so this one, if we had vector A equals 2, 3, and B equals 2, 3, well, obviously, they're both the same. The vectors lie right on top of each other. It's like two vectors with an angle of 0 between them. And so the cosine, if theta equals 0, is 1. And so that's, if you think of it as being like the correlation, they have a correlation of 1. Now, if the two vectors are, let's say, A equals 0, 3, and B equals 2, 0, well, now our vectors are right along the axes here. And so they have a 90-degree angle between them. So it's a right angle. They have a 90-degree angle between them. And then we'd have cosine theta equals 90. Well, that equals 0. And that is a picture of what it's like when two vectors are uncorrelated with each other. So you remember the organic and the regular oranges are highly correlated. So if you graph one against the other, they line up very closely. If you could graph the data in 100 dimensions, or however many observations this is, then what you'd get are, you get a vector of the one vector pointing this way, and if they were totally uncorrelated, so if you had two variables that are completely uncorrelated with each other, and you could graph the vectors would have a 90-degree angle between them. So they'd be pointing not in opposite directions, but one pointing one way and one pointing at right angles away from it. And that's what it means to be uncorrelated, for two vectors to be uncorrelated. And the term for that is they are orthogonal. So when we do matrix notation with econometrics and with econometric data, we use the term orthogonal to mean uncorrelated. We don't say uncorrelated, though, because correlation is kind of a relative term. So when we say two vectors are orthogonal, we mean they are zero correlation with each other. And more specifically, we mean if you could picture the vectors in space, the vectors are at right angles to each other. So orthogonal means, orthogonal does not correspond to this one. This is orthogonal. This is parallel. So the lines are parallel. And going back to this diagram here, but let me just redraw it, because there's one other point to make. 1, 2, 3, 4. And then in this direction, 1, 2, 3, 4. 1, 2, 3, 4. Let's say we draw a vector here. So we'll call that one A, and that's 2, 1. Now let's draw B equals 4, 2. Okay, so pause for a second, make sure you can draw where that vector is. Okay, I will show you where the vector is. You go 4 along in the x direction and 2 up in the y direction. And you'll notice that B lies right on top of A. Okay, if you've drawn your graph so that these lengths are the same, B lies right on top of A. It's just twice as long. It's still going to be the case that these are parallel. So it's still going to be the case that the angle between them is 0. So they don't have to be the same length to be parallel. In this case, B equals 2 times A. In other words, it's just twice as long. Okay, so that is what it means to picture vectors. And again, if you could draw in 100 dimensions and then you plot the vector of organic prices and the vector of regular prices, the two might have slightly different length, but the vectors would be almost right on top of each other. Okay, so let's move to talking about some simple mathematical operations with vectors. Adding vectors. All right, so we'll use, for our example, the first ones, 1, 4, b equals 2, 3. Now you'll notice that in my notation I'm putting square brackets on these, and that is our standard notation. For matrices and vectors, you use square brackets, not round brackets. And also, we usually write them as columns of numbers. You can write it as a row of numbers if you want, but it is more customary to write them as columns. Okay, so adding vectors a plus b, well, as long as a and b have the same number of elements in them, you can add them up. So then we would have another vector now. 1 plus 2 is 3, and 4 plus 3 is 7. So if we have a graph, well, I won't draw it, but actually, yeah, I think I will draw it just to complete the picture here. So we have 1, 2, 3, 4, 5, and we have 1, 2, 3, 4, 5, 6, 7. So let's draw vector A. So A is 1, 2, 3, 4, 5, 6, 7. So it is 1 in the horizontal direction and 4 in the vertical direction. So that is our vector A. And our vector B is 2 in the horizontal direction and 3 in the vertical direction. And then A plus B is going to be 3 in the horizontal direction and 7 in the vertical direction. And one way to think about that is, let's grab a little piece of paper here, is, so we have our vector B, like so, and it starts down here. Well, suppose that we took that vector and we just slide the starting point up the A vector to get to there. Oh, I've messed up my angle a bit. There. So you see we end up with A plus B is A with B tacked onto its end. So you get out to A plus B. So when you add vectors, and you can add them in either order, you get the same outcome. But it's like taking the vector A, and then at the end point of A, you start the vector B. And that's how you end up with the sum of them. Now, I referred to the individual numbers here as elements. So when we talk about the dimension, there are 2 elements. And there are 2 elements in B, and then there are 2 elements in C. So the individual numbers inside a vector, we can refer to those as elements. All right, so that is addition, and you can imagine subtraction. It's the same thing, you just subtract them number by number. Now, I've referred to this earlier example. Where am I? Putting this vector B, so that's A and that's B, and you can see graphically that B is twice as long as A, but we actually should have a proper definition of the length. The length of a vector. And the notation for the length is 2 vertical lines in front and behind. Now, in the notes, in the typewritten notes, for some reason, Word auto-corrected this so that instead of it being 2 vertical lines of equal length, it made it sort of fancy looking, with short and then long. So I know that's what's in the notes, but that's not actually the correct notation. It should be vertical lines of equal length. So how do you find the length of the vector? Well, in this case, what we're going to do is, well, you have to think about the old Pythagorean theorem that you learned in high school. So you remember the length, if this vector here is thought of as the hypotenuse of a triangle, and so this is one of the sides of the triangle, and this is the other side of the triangle, the length here is going to be determined by length of b squared equals 2 squared plus 3 squared. Okay, so you remember for a right angle triangle, the Pythagorean theorem says the square of this side, square of the length of this side plus the square of the length of this side gives you the square of the hypotenuse. And the vector can be thought of as the hypotenuse of a triangle. And so then if we want to know the length of b, we just take the square root of both sides of this equation. So we get the square root of 2 squared plus 3 squared. And in general, that's how you get the length of a vector. You take the first element, so it's 1 squared, and the second element, 4 squared, and then you take the square root of the whole thing. Now, it would also be helpful for examples to have notation. So I could always write A1, A2 as my elements. So then the length of A will be the square root of A1 squared plus A2 squared. So that's the length of the vector. What about multiplying the vectors? So what would it mean to have A times B? So you might think, like, what would sort of make sense would be, using our example, well, we have 1 and 4 in this one, and we have 2 and 3 in this one. So you might want to do 1 times 2 and 4 times 3. That would certainly be a logical thing to do, but that's not actually how to do it. The reason is, and here it's the rationale for how we're going to do this comes from applications in physics. And in the application in physics, if you have two forces working at right angles, they don't combine in the same way that two forces applying partly in the same direction combine. And so the multiplication is meant to measure the extent to which forces will combine. And for that they have to be working in the same direction. So the actual multiplication is referred to as a dot product. So we put a dot between A and B. So A dot B. And the dot product of two vectors, formally, if we were going to do this the formal way, you've got A and B. What you do is you think about projecting A onto the direction of B, and then you scale them by the length of the second vector. And to do that then requires using the cosine of the angle between them. That's not how we're going to do it. That's how you would do it if you were trying to think about if you combine forces that are sort of working in approximately the same direction, what do you end up with? Fortunately, we don't have to do that. The other way, and that's equivalent, is to multiply the elements and then add them up. So if we have examples before, A equals 1, 4, and B equals 2, 3, then A dot B equals 1 times 2 plus 4 times 3. Okay, and so then that is 2 plus 12, so that's 14. So when we multiply them together, we get one number. We do the dot product, we get one number. This operation here, you can do it. There are certainly times when you want to multiply element by element. It's just, that's a different operation. So what we're thinking of for multiplication of the vectors is to form a dot product, and there you multiply the elements and add them up. Now let's take the dot product of two orthogonal vectors, just so you can see what happens here. So let's use as our example, we have 1, 1, and then we'll have another vector that's 2 in the horizontal direction and minus 2 in the vertical direction. So it's down here. So then you can see we get, if I do that better, so these are orthogonal to each other, okay? So then the dot product, so if that's A and this is B, so A equals 1, 1, B equals 2, minus 2, so the dot product is 1 times 2 plus 1 times minus 2, which is minus 1 times 2, so that equals 0. So the dot product of orthogonal vectors is 0. The dot product of any vector with itself would be, well, let's see, A dot A equals 1 times 1 plus 1 times 1, and that's 2. And it's the square of its length. Because if we wanted to get the length, we would just take the square root of that. If we want to get the length of A, we'd take the square root. Okay, so that's enough with vectors. Now let's move on to matrices. So a matrix is a row of vectors. So if we have our vectors A and we have B and we put them together in a row, then we now have, when we think about what the elements are, we have 2 columns of vectors. So if we call that C, then what C is A, which is 1, 4, and B, 2, 3, going back to our initial example. And so C has 2 rows and 2 columns, and in this case it has 4 elements, and its dimensions are written as a subscript on C. It would be written so it's the number of rows and then the number of columns. So it would be a 2 and 2 matrix, and you can put a comma in between to keep it clear. So then we can also use element notation. So let's say that we have, to follow the notes here, let's call it capital A. We usually use a capital letter to denote a matrix and a lowercase letter to denote a vector. So if we have a matrix A, then the first column is going to be denoted by lowercase elements a with two subscripts, and on the subscript, the first subscript always denotes the row and the second denotes the column. So we're up here in row 1, column 1. Now we go to row 2, column 1, and row 3, column 1, and row 4, column 1. And then now we are in row 1, column 2, row 2, column 2, row 3, column 2, and row 4, column 2. And let's just add one more column to this matrix. So we are in row 1, column 3, row 2, column 3, row 3, column 3, and row 4, column 3. All right, so the dimensions here, we will write this as 4, and we'll put a multiplication sign here. Eventually we switch to using letters, and it's a little clearer what the dimensions are, but we'll say it's a 4 by 3 matrix. So A is a 4 by 3 matrix, has 4 rows and 3 columns. And you'll notice that the numbers here reverse when we go diagonally across the center line here. So 1, 3, down to 3, 1. So it's important to, when we work with matrices, it is sometimes important to keep track of whether you're referring to the row or the column. Now, let's say that we had another vector, b4 times 3. And I won't write out all the elements, but they're going to be b11, b12, b13, and so forth, down to b41, b42, and b43. In this case, we can we can add these. So a plus b. And to do the addition, you first check that they have the same dimensions. So the dimensions of A is 4 by 3, and the dimensions of B is 4 by 3. They have the same dimensions, so you can add up the individual elements. So it'll be A11 plus B11. That'll be the first. And then A12 plus B12. That'll be the second along the first row. And then A13 plus B13. That's the third element in the first row. And it'll go down 4 rows, and we get to A41 plus B41. Sorry, that is a mess there. A42 plus B42. A43 plus B43. All right, so the combination, if we call that matrix C, C is also a 4 by 3 matrix. So when you're adding up matrices, you're just adding them element by element. Same if you were going to subtract. A minus B, we'll just replace all the plus signs by minus signs. So with multiplication, if we just want to multiply a matrix by a single number, that's called scalar multiplication. So let's say Z equals 9. Then Z times A is just going to be, we'll just multiply 9 into each of the elements. So it's 9 times A11, 9 times A12, 9 times A13, and so on. So you just multiply the scalar into each of the elements. There's another operation called transpose, And that's where you swap the rows and the columns. So it's kind of like you're going to flip the matrix along the diagonal. So it's turn column 1 into row 1, column 2 into row 2, etc. All right, so if we have, I'll do this with an example rather than fuss with all the little notation. So let's say we have a matrix 1, 4, 9, 2, 3, 2, and 5, 0, 8, and 1, 5, 6. All right, so that's our matrix. A transpose is denoted with the superscript T. Now, some people will write a transpose using A prime rather than AT, and that's okay. I think it's a good habit to use superscript T because when you get into applying calculus to matrices, the prime also denotes a derivative, so it can sometimes be a little confusing. So A transpose, what we do is we take this column and turn it into a row. So we have 1, 2, 5, 1, and then we do the same with the second column, 4, 3, 0, 5, and the third column, 9, 2, 8, 6. So the first thing to note is the dimensions of A is 4 by 3, and the dimensions of A transpose, now they're just the same numbers, but they're reversed. So when you take the transpose of a matrix, the dimensions reverse. Yes, so that's all I need to say about transpose. You're just replacing the rows with the columns, like so. Okay, let's get to multiplication. Because of all the things that comes up in matrix algebra, matrix multiplication tends to be the only one that people get stuck on. When you have a matrix, remember a matrix is a row of vectors. So I'll call these vectors A1, A2, and A3. Okay. So in this example here, A1 is 1, 2, 5, 1. A2 is 4, 3, 0, 5. And A3 is 9, 2, 8, 6. So if I just write it out as the row A1, A2, and A3, that's a matrix. B, another matrix, is also can be thought of as a row of vectors. So how would we multiply A and B together? Well, the key is that we're going to want a matrix of cross products. So the most natural thing in the world would be if we had, so let me write out A1, 2, 5, 1, 4, 3, 0, 5, 9, 2, 8, 6. So that's one vector, or sorry, that's one matrix. And B, say 2, 0, 0, 1, 1, 9. I'm just making these numbers up here. 4, 0, 0, and say 2, 2, 18. If you're going to multiply A times B, it would it would make sense to just think, okay, well then we go 1 times 2, 4 times 0, 9 times 0, 2 times 1. You can do that. That is an operation, element by element multiplication. But it's not the standard operation for multiplying matrices together. When we multiply matrices together, what we want to end up with is a set of dot products. So this vector dot product with this vector. This vector dot product with this vector. This vector dot product with this vector. And but then we can also combine this vector, and this vector, and this vector. So that's what we mean by multiplying matrices together, that we're going to form all the cross products. And it is customary to have matrices for multiplication where you we're thinking of an expression like that, A times B, but we're going to take the vectors out of A in rows, and we're going to take the vectors out of B in columns. So remember, we always think of dimensions of a matrix as rows and columns. And it's the same thing here. We're going to take the vectors as rows and the vectors as columns. And the problem, if we did that, and then we want to form the dot product, well, the problem if we try to do that is we have 3 elements in the first row of A, and we have 4 elements in the first column of B, so that doesn't work. And also we have 4 rows in A, and we only have 3 columns in B. So we would say that that is not conformable. Not conformable. However, if we did this, if we take the transpose of A and multiplied it by B, that would work because then that would be multiplying then we would have we'd be multiplying the 4 elements of the first row of A transpose by the 4 elements of each column in B. And so what we would end up with is try to do it here where I still stay on the camera. So if I have A transpose B, then the first element of A transpose B, so I take this row and I form the dot product with the columns of B, one at a time. So the first one would be 1 times 2 plus 2 times 1 plus 5 times 4 plus 1 times 2. Okay, so that is the first dot product, and that is the dot product of the first row of A times the first column of B. And then I'm going to have the next position along will be the dot product of the first row of A times the second column of B, and then the first row of A times the third column of B, or the dot product. And then for this entry, I want the dot product of the second column of A, or sorry, the second row of second row of A transpose times first column of B. So that's going to be 4 times 2 plus 3 times 1 plus 0 times 4 plus 5 times 2. Okay, so I'm reading across the row here and matching it up with an element in the column here. And so what we will end up with, since we have 3 vectors in A transpose, multiplying them into 3 vectors of B, we end up with a 3 by 3 matrix. So A transpose B will be 3 by 3. And there's a simple way of predicting what the dimensions of the matrix will be. So remember, A is 4 by 3, and B is 4 by 3, and A transpose, since we've reversed the rows and the columns, it's 3 by 4, and B is 4 by 3. And the test that they're conformable is that the adjacent dimension numbers, these ones, they have to be the same. So we know we can do the multiplication because these 2 numbers have to be the same. The outer numbers don't have to be the same, but the inner numbers have to be the same. The outer numbers will give us the dimensions of the product. So if, for example, let's say we had A is 4 by 9 and B is 4 by 3, well, that's not conformable, but A transpose would be 9 by 4, B 4 by 3, and that would be, we would be able to do that multiplication. And in that case, A transpose, it would just have a lot more of these rows, but that's okay because we would just be multiplying by the 4 elements in B, wherever B went to. There we go. So it's a conformable operation as long as the adjacent dimensions are the same, because in that case, then you are taking the same number of elements out of the vector from A as there is in B. So with multiplication, there's a discussion in the notes. So there, I go through A and B, and then the transpose to make it conformable if you need to, and then the product has the outer dimensions. Just one thing I want to show you about matrix B, which you might have noticed when I was writing it out. Notice that this row here, so I'll label the rows 1, 2, 3, and 4. This row is 2 times the first row, and this row is 2 times the second row. When this happens, when one of these rows is a scalar multiple of another row, and the same if it was a column, so if one of the columns was a scalar multiple of another column, then what we would say is the matrix is not a full rank. Full rank. So full rank means that none of the rows can be expressed as, I'll say for now, a multiple of another row. And none of the columns can be expressed as a multiple of another column. I won't rewrite that out, but it's the same thing, that you can't express one of the columns as a multiple of another column. It's actually a little bit more complicated than that. What it means is none of the rows can be expressed as a multiple of another row, or as a combination of multiples of any other rows. So if it turned out that row 4 here was 2 times row 1 plus 3 times row 2, that would also violate the full rank condition. So what we want to have is a situation where you can't express one row as a linear combination of any of the other rows. Now, if we draw a picture here, I'm going to have to do this in 3 dimensions. So what is the first row here? So it's going to just be the vector along this first axis out to point 2, and then at 0 and 0. The third row is just a scalar multiple of that. Okay, so it's just a vector that's twice as long. So that's the gist of one row being a scalar multiple of another row. And then what that means is they're exactly parallel with each other. They're collinear, actually. We've heard the term multicollinearity. Well, this is collinear if they're ones lying right on top of each other. So they have to be independent of each other that way. So all the rows and all the columns. And the way to think of it is the amount of information in the matrix. In this case, you don't actually need all 3 numbers in this row and all 3 numbers in this row to know what the contents of the matrix is. All I need to tell you is the first 2 rows, and then say, well, the third row is just 2 times the first row, and the fourth row is 2 times the second row. So I could just give you the first 2 rows and then 2 more numbers, 2 and 2. So if I could reduce the amount of information in the matrix like that, then it's not a full rank matrix. It means I could simplify it without losing any information. And so the idea of rank is going to be important because if you have a matrix that's not full rank, if it means you could simplify it with some linear operation without losing any information, then it's not full rank. But if it's full rank, it means you need the full matrix to know all the information in the matrix. Now, one more operation that we have is a matrix times a vector. And here it's really just a matrix times a matrix with only one column. And so if we have a data matrix, X, and let's say it has n rows and k columns. So then we write X nk, and we have a matrix, or a vector B, and B has k elements. Well, then XB will have, so that's nk, and B is k1. So B is just a vector with k elements, so that means XB has dimensions n times 1. And you can see an example in the notes of what the multiplication looks like. It's just going to be, the first row will be all the elements in the first row of X times all the elements in B, all added up, and so on and so on. So it's, there's no difference there multiplying a matrix and a vector. It's just like multiplying 2 matrices, but the second matrix only has a single column. Then let's talk about the inverse of a matrix. Now, the inverse of a number is just its reciprocal. So if we have 5 to the power of minus 1, so that's the inverse, and that's 1 over 5. So the exponent minus 1 is just the notation for putting it on the bottom of a fraction. So 5 inverse. And the thing is that the inverse of a number is the number that if you multiply it by the original, you get 1. In other words, 5 inverse times 5 equals 1. So a number times its inverse gives you 1. Now the corresponding concept of the number 1 for a matrix is the identity matrix. And we refer to that as capital I. And the identity matrix is a matrix that has 1s down the diagonal and 0s everywhere else. And it has to be a square matrix. So when we go down the diagonal, we end up in the bottom right-hand corner. So identity matrix, a square matrix, meaning the number of rows equals the number of columns. And the identity matrix, the thing about it is any matrix so A times the identity matrix of the appropriate dimension gives you the matrix A back. And so multiplication by the identity matrix gives you your original matrix back. All right, so the inverse of a matrix then is the matrix that if you multiply by, you get the identity matrix. All right, and or if I write it the other way around, A inverse A equals I. All right, so that's just going back to this concept here. You multiply the inverse of a number by the number, you get 1. Multiply the inverse of a matrix by the matrix, you get the identity matrix. So one thing is this only applies to square matrix. In other words, a matrix that has a different number of rows and columns, this matrix here does not have an inverse because you can't get an identity matrix with 4 rows and 3 columns. So this rule only applies to square matrices. All right, so now how do you get the inverse of a matrix? Well, for that, I'll just have to send you off to take a linear algebra course. There is an algorithm you can follow. There's a couple of different algorithms that you can use, but for our purposes, we would just get it done in a computer. It's actually a very long, laborious process, but it can be done. Only if A is full rank. Only applies to square matrices. Inverse exists only if A is full rank. Okay, so if any of the columns of A can be expressed as linear combinations of the other columns, or if any of the rows can be expressed as linear combinations of other rows, then that means A isn't a full rank matrix. And in that case, the inverse does not exist. So I think that's all the operations now that we need. So we have transpose, multiplication, and inversion. All right. Now, let's apply this to regression. So our regression model is y equals A plus b1 x1I plus b2 x2I plus e. So a two-variable regression model. Let's suppose that y is a vector of observations on the dependent variable, and there are n of them. So y is a vector, and let's make x a matrix. And in that matrix, we're going to put a column of 1s. And then we're going to have the observations on x1. And there are n of them. And the observations on x2. Oops. So I got the notation here wrong. So we are in the first row, second column. That's 1, 2. And I should have spotted that at once because you can't have x2, 1 here and x2, 1 up here. Row 1, column 2 of the x's. And then I'm going to call the coefficient vector beta, and that will be a, b1, b2. And then our error vector will be e1, e2, and so on down to en. So I've just taken the data and represented them as a vector, matrix, another vector, another vector. And now I can write this out as y equals x beta plus e. And this is in matrix notation. So the first row is going to be y1 equals, okay, so let's do the multiplication. So I'm taking the rows of x, multiplying them into, in this case, the beta vector. So it'll be 1 times a plus b1 x 1, 1. I know it's written so the b comes after x, but I can switch the order around in this case just to match up with our notation there. Plus, oops, I have a2 there. That should be b2. You should have said something. b2 x1, 2 plus, and then e1. Okay, so you see we've got the same form back. And if we take the second row, then we'll have a plus b1 x21 plus b2 x22 plus e2, and so on and so on. So that's the same as this expression here, where I equals 1 to n. Okay, so we have now expressed our linear regression model using matrix notation. Why do we do it that way? Why is that an advantage? Because all those really complicated formulas that we had before, where we were trying to keep track of 1 million subscripts and everything was a big mess, they all radically simplify. Beta hat, regardless of how many observations we have, regardless of how many variables we have in the model, beta hat will be x transpose x inverse x transpose y. And you can, if you look at this, you might think, well, remember we had the sum of xi, yi over the sum of xi squared. Well, that's kind of what we've got here. X times y, and then we have the inverse of x times x in front of it. And so this is the way to calculate the least squares coefficients. And one thing that I'd like you to be able to do is confirm the dimensions of this. Okay, so remember x is n by k and y is n by 1 and beta is k by 1. So what you should be able to do is work out the dimensions of this expression and confirm that that whole thing ends up being k by 1. Now, one thing is that when you take the inverse of a matrix, you don't change its dimensions, because remember, you're only taking the inverse of a square matrix. So even if you did reverse the dimensions, it doesn't change. So the inversion doesn't change the dimensions of a matrix. And then the variance of beta hat. Remember before we had sigma squared over the sum of xi squared, and that's only true for the simple regression model. But here we have sigma squared x transpose x inverse. Okay, and the nice thing about doing it this way is now if we use this notation, we're not stuck just with 2 variables in our regression model. You could have 10 variables in your regression model and 100,000 observations, and that's still the formula. So the formula is the same now all the time. And one clever little thing I'll show you, y equals x beta plus e. Okay, now you remember that one of the least squares, or one of the classical assumptions, is that the x's are non-random. The formal way of saying it is that x and e is the x's are uncorrelated with the e's, and that means the expected value of x transpose e equals 0. We haven't seen this version of it. Obviously, we haven't used matrices up until now, but at some times along the way, I've kind of hinted that x's being non-random can be expressed a few different ways, and this is actually what we require, that x transpose e equals 0, the expectation of it. So that would give us the x's and the e's are uncorrelated with each other. So let's suppose that that is true. Then that means the expected value of x transpose and then e can be written as y minus x beta equals 0. So then that means the expected value of x transpose y minus the expected value of x transpose x beta equals 0. And you'll notice that a lot of these operations, they just start to look like regular algebra that you do with simple variables. I can drop the expectations here because we are working with variables where the expectation is its own value. So that means x transpose y minus x transpose x beta equals 0. So now if I take this over to this side, I have x transpose y equals x transpose x beta. And now what I'm going to do is multiply both sides of this expression by the inverse of x transpose x. So then I get x transpose x inverse x transpose y equals beta. And that's my estimator. Okay. We never solved for why it is that that expression gives you beta hat. We didn't do that. You can do that through calculus. But this is another way of doing it here. And this is a third type of estimator that we didn't talk about in the course that's called the method of moments, which means, okay, what are the assumptions that have to hold true if you have the right estimator? And in this case, that's the assumption that has to hold true. And if that assumption holds true, then that's your estimator, and it turns out that corresponds with the least squares estimator. You don't have to know that. You may even wish that I hadn't shown it to you, because maybe you think that's really complicated. But I think it's kind of cool, because it's one of the things that when you get into matrix notation, a lot of derivations that are extremely difficult using the simple algebra actually become much simpler in matrix notation. And so it would have been very difficult for us to write out the method of moments derivation of the least squares slope estimator if we tried to do it in our original notation. But as you can see here, it ends up being kind of clean and kind of neat. So that is how we're going to do least squares in matrix notation, although we're not going to do anything with it because we're at the end of the course. And but this is more like what the computer is doing. It's doing matrix operations on the data rather than the subscripted notation. And then if you go on, as I say, when you go on, as I hope you will, in econometrics, doing like econometrics of finance or any advanced labor economics, you have to use the matrix notation in order to develop the techniques further. And there, we're done. All right, go get yourself a cup of coffee or a beer or something and toast yourself for having got this far. And next lecture will be a review.